Hi everyone, this is Sarah DeMeo with Acuity Solutions, and welcome to our first part of our 5-part webinar series, How to Expand Your Business with NX for Manufacturing. We decided to put this series together because we are finding that today's manufacturing climate is changing rapidly. I would be willing to bet that you are likely experiencing at least one of these challenges in your business today. You might have more complexity in your products. You may have shorter lead times. You may be introducing prototypes into your design business. You could be doing short-run production in a job shop, and it's very likely that you've got multiple systems that don't talk to each other, thereby reducing your efficiency. Today, our Andy Schaefers is going to show you how NX CAM's advanced 5-axis techniques will give you smoother toolpaths, more throughput, and greater flexibility, resulting in clean, reliable G-code. The first topic we're going to cover today is Swarf machining. Take it away, Andy.
What NX has done is take some complex 5-axis machining techniques, but develop algorithms where they're very easy to implement, so they require less training and less user intervention. Here I've got a part that I'd like to swarf machine the outside surface on. You can see that it's got a convex curve on it, so I'll create an operation. And rather than choose the automatic walls, I'll just specify this as the wall that I'd like to machine. Then we'll go to cutting parameters, and I'll tell NX that I just want some multiple depths to machine here.
So Andy, what's going on right now while you're putting this operation together?
NX is just looking at the geometry, the floor that I've specified, and now it's giving me cuts at these multiple depths.
Oh, interesting. Okay.
So what I'd like to do now is just verify and if we look closely, you can see that there are little steps here as it goes from one pass to the other. Because this is a convex curve, it's going to leave those steps on there. But in NX, we have a way to remove those. This is called a ring height. And what we'll do is drop the cutter down the convex surface by a certain distance. So now when I regenerate, I get those same passes, but they're deeper down. So let's verify again. And you can see that the passes are now overlapping each other. So I've got a very smooth finish that's going to require just minimal bench work to complete. So that's a huge advantage, is this ring height machining we have when we swarf drive that is very easy to implement with just a few settings. And in many other CAM systems, it's very difficult to create a toolpath like that. Here's another example of swarf drive type machining using our variable contour operation. If we look carefully at it as we just run the cutter down this existing pass, you'll see that the tool axis is changing pretty aggressively from one end to the other. This is our default for our tool axis. It's just automatic mode. What I'll do now is change it to align to edges. I'm regenerating the path, and now you can see the difference. Rather than have that tilt in at the beginning and the tilt out at the end, the tool axis is now following the edges of the part itself.
Even though they're not necessarily straight or easy to be machined? Because I can see that there's some inconsistencies just in the wall there.
Right. So sometimes in other CAM systems, the tool is going to want to follow the UV direction of the surface. That's an internal designation of the surface. We can do that, but in NX we can also tell it explicitly to follow whatever edges are modeled on the part.
Very cool.
And that saves the user time because there's a better workflow for them?
Well, the benefit here is that in NX you're not forced to accept a tool path that's going to be hard on the machine or the tool.
So we can get to an optimal tool path more quickly.
Yeah, in a lot of other CAM systems, if you can get it machined, you're just going to take what you can get and go and run it. And that's a tool path that may not optimize your tool life, your surface finish, your accuracy. In NX, you can get to that optimum tool path with many more tools than other CAM systems have.
Now let's talk a little bit about Turbomachinery.
Many of our customers have told us that they need to be able to machine turbomachinery components like the one you see here on the screen. And we've developed additions to our 5-axis machining techniques to help them do that. The goal for them is not just to be able to machine these parts, but the fact that the order quantities are very low. Sometimes only one part will be ordered, and so the part must be programmed very quickly and run efficiently, or it's not going to be a profitable job. So here are some of the extensions that we've made to our existing software to help with that. If we look at our geometry view here, you'll see that to set up a blisk like you see on the screen, we specify the hub, the shroud, which we've specified by picking up only one of these faces, and then one of the blades, the blade blend at the bottom, and then here's a splitter, the smaller blade, is also defined.
Okay.
By defining only that geometry, we're then able to apply our specific operations. And so here you're going to see Swarf machining and a couple of our other techniques. So here we're using a blend finish on this the side of the blade. I'll just run the verification real quick so you can see it. And so this is not, as you can see, just a ball end mill. It's a tapered ball. And the reason for that is we're getting into some very tight, deep spaces. We need the most rigid tool possible. So we're using a tapered ball to improve the rigidity. I'll speed this up here in just a second as soon as it gets to the end of the move. So we're using a technique very similar to the last example with the contour profile, where we're now just working our way around that blade. So that's an example of the Swarf machining. Then we can go into the hub finish, and here it's automatically working between the two blades, and it sees the splitter, and it's giving us a smooth tool path. Again, it's constantly aware of the rest of the part, so we're able to use a tapered ball end mill and keep our stiffness up.
Okay. Now how might people be handling this today?
Well, there are different approaches, but typically they're just using whatever 5-axis techniques they've got and doing the best they can with it. So you can pick out a part like this, and you'll get there eventually. You'll just have a lot of inefficient tool path, and you won't always be able to run these stiff cutters, so you're going to have to take lighter cuts, and your cycle time will be much longer.
Okay.
Also, it's very difficult in other systems to make money on just this one or two parts. You need a longer run because there's so much programming time involved.
Tilt tool axis is Andy's favorite. We'll show you 3 different ways that this new feature can decrease your cycle time and improve your tool performance. We'll also chat about how NX has made it easy for you to program your complex operations.
Many of our customers are just moving into 5-axis machining from a 3-axis environment, and they're looking for a way to get started with 5-axis. It's not going to require a lot of training or investment on their part. The tilt tool axis is a great technique for them to jump into 5-axis. Here we have an example of a toolpath that was made using a very simple technique of just tilting the tool away from the wall by a particular angle. And as we look at it, we'll see where the problems are in this toolpath. So if I click on some other toolpath entities, you'll see that all we're doing here is tipping the tool away by an angle. I think it's 25 degrees. So that works fine up here at the top. But as we get farther down and we get into this notch area, we're having troubles. The tool is actually crashing right here because that simple technique does not work with this complex geometry. So the tilt tool axis command is one where you just take an existing toolpath that you've made. It can be a 3 or a 5-axis toolpath, and we give it an additional tilt based on the actual geometry. So rather than the programmer making decisions about where the tool needs to change, we're letting the software make those decisions. So here is an example of a toolpath that's been tilted. Let's look at it. As we get down to these lower passes, you can see that the software has realized that it's got to tip that tool out the other direction to prevent it from colliding. So this is actually a very complex situation where it's looking at the tool, the shank that you see in green, and then the holder that you see in the orange color, and it's looking at all the geometry of the part to make sure that that tool will fit.
And it literally automatically adjusts for it.
That's right. Now let's look at an example of tilt tool axis with where we start with a 3-axis toolpath. So here you can see that we've got, because of this overhang, a situation where our tool is going to collide as it gets into this wall down here. So with a 5-axis machine tool, of course, we can tip, that's a little too fast, we can tip the tool back away from the wall, but what's the best way to get to that program? The tilt tool axis is a great solution to this. Let's look here at a toolpath that's now been tipped. And the green lines that you see on the screen are an integral part of this. We are using those as a hinge point. So as the tool comes back out and hits that hinge, it rotates. If you concentrate, you can kind of see how it's hinging right about that point. What's the advantage of doing that? Well, often 5-axis machine tools are limited by the speed of the rotary axes. So if we came out of this little waterfall area and then did the rotation all at once, it would slow the tool down through this area. What we want to do is create a fan where the rotation occurs over a much larger area of the tool path. And that's what we're doing here with the tilt tool axis and our hinge point. We're giving you the most efficient tool path possible by fanning over this wide area. So again, we just took a 3-axis tool path that most shops programmers already know, and just by tilting the tool about this hinge point, they now have a very functional 5-axis tool path that's going to run efficiently on their machine tools. Okay, so another use of the tilt tool axis is in a cavity situation like you see here. We'll start with a 3-axis tool path and then convert it into a 5-axis tool path using tilt tool axis. Here's the surface that I want to machine. And rather than zigzag, I'm going to choose to follow the periphery. And we'll cut inward. No, I'm sorry, probably cut outward. So we'll start at the middle and we'll cut outward. Okay, so what we have now is a toolpath that's just spiraling around to finish the cavity. It's a very easy to create toolpath, but of course as we get towards the outside, you can see that the holder of the tool crashes on the tall vertical walls. Let's now right-click, choose toolpath and tilt tool axis, and we'll just give it a maximum angle here of 20 degrees. And it thinks about this for a few seconds as it looks at every motion in reference to the wall geometry and tips only the areas that need additional clearance. Okay, here's our result. And it doesn't look any different here in terms of the center line of the toolpath, but if we go into the operation and verify, here in the middle where there are no clearance issues, the tool axis is still vertical, just as it was before. But watch what happens when we get to the outside. Here, where it's necessary, the tool is now tilted to provide for clearance. So this is an excellent technique for finishing a floor like this, where you're running your tool axis vertical everywhere you possibly can, because that's always going to be your fastest tool path, and then it's only tilting in the areas where it's required. It's an excellent and simple solution to the problem.
Tell us a little bit about, what NX has done to make it easier for the users to pick it up and customize kind of what they do.
Okay, well, first of all, I think what you'll see in NX is a combination of a well thought out interface, adherence to the Windows standards for how the interface looks, so the interface should look familiar to you if you've used other Windows products, and also really nice interactions and power with the objects that are here in what we call our Operation Navigator. So I'll just go through a few changes so you can see what you can get done just using simple drag and drop techniques. I'm going to look here in our program order view, and you see this single operation that we've made. Well, if I want that to be in a program that I'm going to output, all I have to do is drag and drop it. It now is a child of that program, and when I post-process it, I'll just select a post here. It's going to go look at my operation, and in a few seconds we'll see the G-code appear on the screen. So now we've just output a program. Now let's go on to the machine tool view, and you see I've got just a single tool with our operation. It's very easy to make a second tool. I can come up here where it says create tool and make another ball end mill. I get a visual reference on the screen. I've got parameters I can key in here. If I want to see where this tool is on the part, all I do is drag and drop it onto that surface, and I get some feedback about, is that tool going to fit properly in there. If I want to put a holder on here, I can either key in values for a holder, or I can go off to the library. And let's stick a holder on here real quick. And now we see the tool with the holder.
Okay.
Now if I want to change this operation to be using this ball and mill instead of this one, all I've got to do is drag and drop, and it's now a member of that other tool. Let's go on to the geometry view, and here again you get a nice visual reference of all the objects involved in the geometry for this program. Here's the MCS, or our machine coordinate system, and this is exactly your G54 or G55 coordinates on your machine tool. If I want to move this around, I can key on an exact point, or I can key in, based on selecting the axis, an exact value. So I'll move it 2 inches out. So there's just a lot of flexibility here to rotate or move this coordinate system to the place it needs to be. Then I've defined my workpiece. It's just the block as you see it. And I can also define a blank here, or check surfaces, which could be a vise or your clamps. Then in the method view, I select all of the stock offsets, feeds, and speeds that I want to assign to a tool. So if I want to change this from being a mill finish to a mill semi-finish, all I do is drag and drop the operation to another method, regenerate, and the new settings are now taking effect. So there's a lot of power here, but I think you can see that just using drag and drop and simple key-ins, you've got excellent control over all of the options involved here in machining. Okay, here we'll talk about our geometry selection techniques. We're looking at a cavity shape in this block, and our intent then is to machine only a small portion of this. So the question is, what's it going to take to filter out only the faces that we want to machine? We've got several techniques for doing this. Here I'll create a geometry entity called mill area that represents just some of the faces I want to machine. So here I'll choose specify cut area, and my technique I'll use is called edge bounded region, where I'll select first a seed face, and then I say, well, here's the bounding edges, which could be this perimeter here, and then say this perimeter here going around the inside. When I click OK and hit the torch, you see that it's selected only those particular regions. So it's used the seed face and the two curves to give me the region I was looking for. So it's a very powerful technique to select by your intent rather than having to select all those faces individually with mouse clicks.
Finally, we'll show you how you can optimize the drive path on your complex surfaces.
In this example, we're simulating a large tool that we're machining as an aerospace mold surface. The tool has been rough formed using either cast or welded together sections, and what that means for us is that the amount of stock that's left anywhere on the tool is variable. However, because it's a large tool, we don't want to be doing a lot of air cutting, so we want to be able to machine only the areas that have extra stock while we're roughing our way down. So we've scanned the actual tool surface as it existed when it was welded up, and that's the stock that you see here on the screen in blue. But if you can kind of look carefully, you can see that there's a lump here and a kind of a lump over here where there's extra material. So those are the ones that we want to machine separately. Our other goal here is that we're using a tool that's going to be more efficient for this type of operation. I'll show you now. It's just a bull nose cutter, so it's flat with just a small radius, a 30 thousandths radius on it. We want to keep that tool normal to our part, but tip the heel up slightly so that the heel never hits. Here's the operations that allow us to do that. We're going to change our tool axis algorithm to optimize to drive. Here in the settings, I've got a 7 thousandths heel clearance and a maximum lead angle of 25 degrees with a nominal lead angle of 6. What NX is going to do is look at that geometry and figure out automatically what the step over needs to be to provide the ultimate result that I'm looking for the finish of the tool. Also, it's smart enough to look at the stock and only add passes where required. Here's where that's set up. We have the multiple passes set here at a depth for each pass of 1/4 of an inch. But because it understands where the IPW or the in-process workpiece is, when we actually finish it, you can see that the toolpath puts extra passes in where the two lumps of material are, but not in other areas. Let's quickly look at a 3D dynamic verification of this. So here it's removing this stock in 2 passes, and then you'll see it start to go larger as more and more stock is involved in the cut. Finally, we get to the finish pass. That's a separate operation here. And rather than specify a step over, I've specified a scallop height. And NX is sophisticated enough to look at that bullnose cutter and figure out what the step over will be with the tilt angle and the scallop height that I've given it. On a large tool, these techniques can save a lot of time in machining. You'll minimize your air cutting, and you'll maximize the step over that you can use and still get the finish that you're looking for in your tool.
Thanks, Andy. So that's all we have to show you today. We invite you to come back for parts 2 through 5. As you can see here, on March 18th, we'll show you our integrated simulation and verification as a possible alternative to Vericut. On April 1st, we'll talk about NX's tight CAD and CAM integration and show you why that might make sense for your company. On April 15th, we'll talk about NX on-machine probing to automate the process of programming your Renishaw probes. The series will end on April 29th with an in-depth look at NX CMM, our integrated CMM programming solution that can save you up to 50% in programming time. Thank you all for attending today. I hope you found this 30 minutes valuable, and we do hope to see you at one of our future webcasts. If you'd like to reach us before then, feel free to give us a call or send an email we've got the phone number and email addresses listed here on the screen. And also be sure to visit our website at www.acuityinc.com. Now, I'll open the lines for any questions you might have for Andy. Thanks, everybody. Have a great day.